The last collection of trig identities that we're going to look at are the sum difference formulas and the double angle formulas. So I've got the sum difference formulas written there. I'm not going to provide a proof for these. You can just find them on the internet. They're a little bit more tedious to go through than, for example, the sine and cosine laws, but they are legit. One thing that is nice about sine and cosine, or the trig functions, is that we actually do have a formula for splitting addition. For example, like, remember, we couldn't split up logarithms when there's addition on the inside. There's no way of pulling that apart. We know, like, roots, for example, we can't do anything with that. But sine, there is a formula. It's not for free. You don't just split it up or distribute the sine. But there is a way of dealing with it. The subtraction formulas, so they actually just come from using the additive formulas. So if you actually wrote like sine of a minus b equals sine a plus negative b, and then if you plug the negative b in the place of the b in actually all of the formulas. So if you remember the symmetry rules, the cos of negative b actually would just stay as cos b. And then the sine, oh, sorry, I've got that one on the a, not the b. The sine of negative b, in that case, that's where the minus is coming in. It flips that sign. And then the same thing on the cosine one. The first term stays the same because cos of negative b is the same thing as cos b, but the sign is going to flip signs. And so, yeah, that's just sort of how the formulas work. You guys don't have to memorize anything, though, so you shouldn't be too worried about it. All right, so I'll start with a question here. So there's really two ways that we can use these formulas. One of them is if you're already provided some kind of nice set of information, we can use it to figure out something about the sum of those two angles. So kind of exactly what I've got here. Cos A is 12 over 13. Sine B is negative 4 over 5. We are also told what quadrant A and B are in. That will actually be necessary. And so what we want to do is find sine A plus B, cos A plus B, and tan A plus B. All right, a good place to start would be to actually write out some of these formulas. So let's say we start with sine. So sine of A plus B, well, I'm going to write out the exact formula for sine of A plus B. So sine A cos B plus sine B cos A. And we actually have two of these values already. I've got cos A and sine B. So sine B is negative 4 over 5, and cos A is 12 over 13. And the problem now is that we haven't figured out these two. We don't know sine A cos B, but we actually are provided enough information to do this. Because I know sine and I know what quadrant it's in, I should be able to draw a triangle on the xy plane and figure out the third side of that triangle, which will give me all the other ratios. So for example, for A, cos A is 12 over 13, and it's in quadrant 4. So that tells me that it should look like 12 over 13. The Pythagorean theorem, if I solve this triangle, I'll get 5 for the other side and negative because it's downwards. And so that tells me that sine A is negative 5 over 13. And then similarly, I know sine B is negative 4 over 5. And it's in quadrant 3. So negative 4 over 5 should look like this. And then the other side of this triangle would be a 3 and a negative 3 because it's on the left side. And so that tells me that cos B is now negative 3 over 5. And so I get to just plug those in. This is actually all the information that I need to do everything for the rest of this problem. So my sine A is negative 5 over 13. Cos B is negative 3 over 5 plus negative 4 over 5, 12 over 13. And we should be able to clean this up. So 15 over 65 minus 48 over 65 equals negative 33 over 65. Okay, and then we'll do cos of a plus b. So again, just write out the formula to get this started. Cos a cos b minus sine a sine b. And I already figured out all of that information. I just did it for sine. So cos a is 12 over 13. Cos b is negative 3 over 5. Sine a is negative 5 over 13. Sine b is negative 4 over 5. So I get negative 36 over 65 minus, it's a triple negative, so minus 20 over 65 is negative 56 over 65. And then tan, well, I didn't give you a formula for tan, but we can use one of those previous identities. Tan is just sine over cosine. And we know the sine and cosine. We just figured that out. So I'm going to get negative 33 over 65 over negative 56 over 65. And then we can just multiply the top and the bottom by 65. And the negatives will cancel. We get 33 over 56. So those are my three answers. And then what you'll notice is they actually are all rationals. So even though we were dealing with Pythagorean identity and square roots, we didn't get any. This is actually very closely related to a formula that you can use to generate Pythagorean triples. So these nice integer solutions to the Pythagorean triangle. You can actually just like add these types of angles together to get bigger and bigger solutions to the Pythagorean theorem, which is kind of cool. Yeah, so we'll do one more different type of problem. Okay, so now what we're going to do is find the trig ratio cosine for 7 pi over 12. So we've got all those special angles that we've seen before, but they are like fractions over 2, pi over 2 are multiples of 90. Fractions over 3, pi over 6 is multiples of 60. Pi over 4, 45. Pi over 6, 30. The ones that we're able to do using our special triangles have denominators of 2, 3, 4, 6. What we've actually got here is 12. This is not going to be one of our special angles. If we actually look at this, it's 105 degrees, right? Yeah, 15 times 7, 105 degrees. If we draw this, it'll come over here and have a reference angle of 75 degrees, which is not one of our special angles. So we can't get this exact ratio without either using a calculator, which I want to avoid, or using the sum or difference formulas. So I'm going to add a little exact value here, just to say I don't want like a decimal. I don't want you to plug it in your calculator and spit out a decimal. I want that algebraic exact answer. So what we need to do is find a way to express 105 degrees as a sum of angles that we can actually figure out. So a sum or difference of multiples of, and so what I'll do is use 30 and 45, because 30 will cover your 60 and your 90 and then all those multiples, and 45 will cover the 45s and the 90s. And then we should actually be able to get to any multiple of 15 using these combinations. And so in particular, 105 degrees, there's a few ways we could do it. We could do 60 degrees plus 45 degrees. We could do 150 degrees, which is 5 times 30 minus 45 degrees. We could do 3 times 45 is 135. Yeah. We could do 135 degrees minus 30 degrees. There's lots and lots and lots of ways that we could do it. I'm going to just choose this one here. So I'm going to write cos of 7 pi over 12 is going to be equal to, so 150 should be 5 pi over 6. And then minus, sorry, I don't want to close that bracket yet, minus pi over 4. Right, so that's my 150 minus 45 degrees. And yeah, so that should, like if you actually work with the fractions and common denominator, you should get 7 pi over 12 there. And so now what I'm going to do is just use my corresponding cosine formula. So it's the subtraction. It's going to be cos A minus B. And in this formula, my A is the 5 pi over 6. And my B is the pi over 4. So I'm just going to swap those in for the formula for the difference of cosine. So it'll be cos 5 pi over 6 and cos pi over 4 plus sine 5 pi over 6 sine pi over 4. And then now we just use special triangles to figure these values out. So if I do pi over 4, we know that one, that's just 45 degrees. So that should be the 1, 1 root 2. So my ratios, sine and cosine, are just going to be 1 over root 2, 1 over root 2. So I'm going to plug those in. And 5 pi over 6, so that one is, that's 150. And that has that reference angle of 30. And so if I draw this one, would be my 1, 2, and then root 3 triangle. And just remember that is a negative root 3 because it's on the left. And so I should have sine 5 pi over 6 is a half. Cos 5 pi over 6 is negative root 3 over 2. And so we can plug those in. So cos 5 pi over 6 and sine 5 pi over 6. And just multiply it all out. So I get negative root 3 over 2 root 2 plus 1 over 2 root 2. So I'd have 1 minus root 3 over 2 root 2. So I would be okay with this answer. You might find the textbook or whatever reference you're using might clean it up a little bit more. So they would rationalize the denominator by multiplying the top and bottom by root 2. And then a different way of writing this answer would be root 2 minus root 6 over 4. And so, yeah, same answer. It's just some of you might have a scientific calculator that will actually display kind of like this version, or if you're checking answers in the textbook. But yeah, so this actually now allows us to get the exact trig ratio for any multiple of 15. Before we were limited to 30s and 45s. This gives us a bunch more. So it does, allows us to do a little bit more without a calculator, but it's not that powerful in that regard. I like the first question a lot better.